Okay, great. Ah, all right. Okay. 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 All right. Who's here? Anyone here? No one's here? RDL? Okay. Um, so this week, we begin with perhaps. So we begin with fundamental theorem of algebra. I'll prove it mostly. Leave some easy details out. But the first thing I want to say about what's in the book. So the book is the 4th edition, and when I read the book a long time ago, they had a different proof, using something called the winding number of a complex valued function. Okay? And that's a well-known established theorem proof. And it has the benefit of being correct. Now, I don't know why he switched to this other proof, but the proof is, I mean, I was preparing for class and I started reading it, and has a important error on like the third line somewhere. Then I frantically went, he says it was on Wikipedia, so then I went on Wikipedia, and I don't see this proof there anymore. Okay. Probably because someone caught the error. And so unfortunately it made it into print in this 4th edition. And now, so don't read that proof. Don't read the first part of the proof. I'll salvage it, and then the latter part is fine, is totally fine. Okay? There are so many different proofs of this theorem, and this one is kind of the one that requires the least amount of specialized knowledge. Okay? So, that's what we're going to prove, the fundamental theorem of algebra, and then we'll see what, then we'll talk about random things afterwards. Okay? So that's the main topic for today. All right. Hi, Ella. Hi, Ella. Hi. Okay, let's begin. 3-part lectures, as usual. I'll start by defining what an algebraically closed field is, just so we have a definition to think about. And then the theorem, the fundamental theorem of algebra, which, by the way, is not fundamental, but it's cool. It's very good. Nice theorem, but it's not like you don't need it for many things. Is that like it's not it doesn't rest in the foundations like, you know, group theory does. But it says that the complex numbers are algebraically closed. Okay? So that's what we're gonna do. So let's do the first part. Easy. Definition. A field is algebraic. You know what a field is. System of numbers where you can have division. Hi, N Burrows. How's it going? Oh my god, N Burrows, celebrity in the house. You know what a field is. Go review it right now while I shout out our friend here, N Burrows. Teaches chemistry. Go check him out. A field is algebraically closed. Okay? If every non-constant polynomial with coefficients in f has a root in f. In other words, every polynomial, one variable polynomial equation, which is not just like a constant equals 0. Every positive degree polynomial equation with coefficients in the field has a solution in that field. Okay, so Q is not algebraically closed. Because here's a polynomial. Coefficients in Q does not have a solution in Q. That's the legend of Pythagoras' student. And then Pythagoras threatening hanging them or whatever. Right? The real numbers are not algebraically closed. Because of the equation, for example, or, you know, I mean, whatever you want. X squared plus a positive number. Yeah, this is has no real solution. Root. Root means set it equal to 0. Okay? And so now we can state our magical, our beautiful theorem. So here's the beautiful theorem. We're going to start 2 now. So incredible. It's a theorem that not at all obvious. So beautiful theorem. It says that the complex numbers are in some sense the end of the road when it comes to this evolution of number based on introducing solutions to polynomial riddles you couldn't solve before. Complex numbers are kind of like the end of the road. Or, yeah. So the theorem is the complex numbers are algebraically closed. Now, this theorem has a long history. You can read about it in the book. And I think the first person to actually give a correct proof is Gauss. And I think this was, if I remember from the book, I think this was the subject of his PhD. Okay, pretty good. Not bad. Not bad. Not a bad start, gotta say. All right, so he then went on during his lifetime and produced many other proofs of the same result in different ways, okay? Anyway, so we're going to prove it one way. I don't know how many different proofs there are of this thing. There's a bunch. But some proofs use more sophisticated ideas than others. And this one is nice because it uses kind of more elementary facts from real analysis, okay, and topology. Okay, so before I start on the proof, every single proof involves some kind of either real analysis type fact or continuity type principle. And so it's not really purely an algebraic proof ever. You'll use some notion of continuity in some form, like continuous functions that you don't lift your pencil, like that. Okay? By the end of this class, we will see probably the most algebraic proof available. There's a proof that uses Galois theory, Sylow subgroups from group theory, and then one little bit of continuity principle that an odd degree polynomial has, over the real numbers, has to cross the x-axis somewhere. Intermediate value principle or whatever. That's the most algebraic proof. That'll come at the end, after we learn Galois theory. It's a little advertisement. So this one we're going to have... We can't use Galois theory here yet, so we're going to look at the most elementary type of proof. Okay, the book has an important error, and I'll try to point it out. So here's let's begin the proof. And some parts of the proof I'll sketch, and other parts I'll focus on. Okay, so here's how the proof goes. Let's give a name to a polynomial over the complex numbers that we're saying has to have a root. So this is a polynomial, and here's its constant term. Here's its and if we're saying that a polynomial has a root, you might as well has to have a root. You might as well assume that the top coefficient is 1. You don't have to do this, but just assume it for simplicity. Let's call the top coefficient n, so that I don't mess up my notation. So you can just divide out by the top coefficient and pretend that it's 1. Okay, so here's our polynomial and our goal. And we know that n, we're assuming n is bigger than 0, of course. Not a constant polynomial. all the coefficients are in C, complex numbers, and the goal is to argue that there is a zero of this that there's a root of this polynomial. That's the goal, to produce a zero. So here's the idea. The idea is to study the norm function. Take a complex number, plug it in, and measure its norm. This is a function that goes from the complex numbers to the real numbers. And yes, it lands in the positive real numbers. Positive or zero, right? So the idea is to study this function and proceed by contradiction. Okay, so study this function and proceed by contradiction. Okay, so the first thing that the proof wants to establish is that there exists a complex number which realizes the smallest norm. That's the bit that has an error in it. Okay, in the book. Okay, so we're gonna proceed here with this strategy. So step one is to establish that there exists a particular complex number which realizes the smallest norm. So for which P of the output is the smallest size complex number among all outputs. So that part has a problem in the book. And the way the book proceeds is it says this. So the book says this. Now I just want to point this out here. The book says this function is continuous. That's correct. Okay, you can write it out and you see it's just a continuous function in the 2x plus iy, the x and y in z, in the complex number z. So that's a continuous function. That's correct. Okay. But then it says, so then it wants to use the following fact. It says that the inverse image, or the pre-image, of a closed interval, and I think they use some particular interval, I don't know, whatever, it's a closed interval, is compact, is a closed and bounded subset of C. Okay, this does not follow from a function being continuous. All right, so like the function r to r given by x goes to e to the x. All right, I want you to think about that example and notice that the inverse image of a closed interval, need not be a compact subset of the domain. All right, pre-image of a compact set doesn't have to be compact for a continuous map. What is true is that the image of a compact set under a continuous map is always compact. So the real analysis fact that we can use here, that we will use, but it's actually a fact in topology, is that the image of a compact set under a continuous function is compact. Okay, that's what we can use. We will use at some point. All right. So our goal is, again, to realize that there is a point whose output norm is minimized. We want to invoke that point and then arrive at a contradiction afterwards. So to do this, you have to use something, you have to use a lemma that's often called the growth lemma. Okay, so to get to this goal, we have to use some cleverness. Okay. So what we have to use to like fix this error in the book is the following fact. Okay, this fact will come out of the triangle inequality. Which I'll review for you what that says just in a second. But what we use is this. There exists a huge radius such that our polynomial function, its size, let's just not put a square anywhere so it's more visually makes more sense. Its size is more than half of just the size of z to the n, the like largest term. It's more than half of that, but less than some other constant times that. It's sandwiched. Okay? What this is saying for all complex numbers beyond that radius. Okay, so what it's saying is that when you look at a polynomial function, if you start putting in complex numbers way out far towards infinity, the outputs will also have to be really, really big. For example, in particular, they'll also have to be really, really big outputs. So in other words, a polynomial function has to grow in size, in magnitude. The outputs have to grow in magnitude after a certain point. They have to at least be this big. And this thing grows fast, right? This thing is growing like radius to the nth power. All right, so that's what you have to use in order to establish this minimum, the existence of this minimum output. Okay, so in order to prove this, I'll just tell you what to do, what the ingredient is for this proof, and then you can try it. So to prove this, you use the triangle inequality for triangles in the plane. So you use this. If you have two complex numbers and you look at the magnitude of the sum, it's less than or equal to the two magnitudes combined. And you're going to apply this in some clever way to this polynomial where you think of it as this part plus the rest. Remember, the coefficients are some fixed numbers. These are fixed given to us. So those things aren't changing. So yeah, use the triangle inequality for the polynomial and you can establish this this fact. Also, use the obvious fact that like the norm of z to the n is bigger than the norm of z to the n minus 1 if the radius is bigger than 1, for example. Okay, so that's the actual little bit of analysis. Sorry, a little bit of triangle inequality type math, which is complex analysis type arguments that you have to like invoke at a certain point in order to establish that there is a particular place which minimizes the norm. There is an actual number that minimizes the size of the outputs. All right, so how do you get to that, establishing that? So from this fact, from here, it follows that there is an enormous circle. Let's say, you know, around the origins, it's just a big circle in the complex plane. Such that so big circle means big closed disk. Okay, such that for any z outside of the circle, the size of P of z is bigger than the output at some point, any fixed point that you'd like inside the circle. Let's say 0. Why? Because P of 0 is a particular number and it has a particular size. But after a certain enormous radius, the size of all the outputs is bigger than 1/2 times the radius to some power. Huge. And that huge number is bigger than the size of P of 0. So outside of here, all the magnitudes of outputs are bigger than some particular magnitude in here, of some point in here. Okay, some particular fixed one that you'd like. And therefore, oh, let me say another thing. So that's one thing. Second thing, the closed circle is a compact set. And therefore, the magnitude function realizes a minimum. For some point in that compact set. Now that minimum has to be the global minimum, because that minimum has to be, for example, in particular, less than like whatever this random one was. And that is less than the size of all the outputs outside of the disk. And so this is why there exists a global minimum for the magnitude function. You have to use some knowledge that the function grows outside of a big radius. And so you can actually get like a bowl shape Calc 3 situation. That's what's the essential ingredient that's missing in the book's proof. Very important, because it's like, it's totally not a good start. False start for the proof. Okay. So yeah, I had to fix that frantically this morning. So I'm not really happy about that, but it used to be right in previous editions for other proofs. Okay, so now let's proceed with understanding that there is some global minimum for the magnitude function. So if you didn't like that, forget it. So let's just proceed now with the understanding that there is a global minimum for the magnitude function. Minimizing the magnitude. And yes, I keep putting the square there because algebraically it's easier to deal with the norm than, because you don't like these big square roots everywhere, okay? So if you minimize the magnitude, it's the same as minimizing the norm, of course. All right? And we're going to proceed by contradiction. So assume this minimum is bigger than 0. Strictly. Right? Otherwise, if it's 0, then then z0 was a root. So assume that it's bigger than 0. And what we're going to do is we're going to do what the book correctly draws a picture of. We're going to sort of wiggle z0 and argue that there's a direction you can wiggle it. Direction because we're in complex plane now. Which reduces the magnitude. Strictly reduces the magnitude. All right, so that's the idea of the rest. The rest is correct. You can read it in the book. All right, so I'm going to simplify things. I'm going to simplify. Okay, so this is what we will contradict this thing. All right, so to simplify, we might as well assume that this z0 is just literally the number 0. Because you can do a substitution that shifts the complex plane. Yeah. So assume z0 equals 0. All right? And now I'm going to write out the polynomial again. And let's study it carefully. So it has a constant term, which is a complex number. And then we're going to sort of search for the first non-zero positive degree term. So it's going to go, maybe it has no linear term, maybe it has no quadratic. And then we're going to call this the first term. I'm just following the book now, so you can, except I made this simplifying assumption that is totally fine. Okay? So, and this is like, okay, I don't know if m plus 1's coefficient is non-zero, but let's just write the rest of it. Okay, we're pretending it has, it's got no top degree term. That top degree term being, having top coefficient being 1 is only used in this inequality, just to establish this. Just look at the triangle inequality thing that you'd have to establish. Okay, good. Great. So let's write it out like this. This is a non-zero coefficient. And we know that this is also non-zero. Because after all, then P of z would have a root, namely z equals 0. And we know that when we plug 0 in, you get the smallest magnitude output. Okay, so P of 0 is then just P sub 0. And the magnitude of that, or the norm, is P0 times P0 bar, right? The norm of any complex number is that the number times its conjugate. We're going to use that all the time. And that's why we like norm better rather than putting a square root and talking about magnitude. Fantastic. Okay, so that's what we know. And this is the smallest norm of any output by hypothesis. We're pretending. And that it's a positive number. Okay, so in particular, P0 is non-zero and Pm is non-zero. And now what we do to this polynomial is we plug in complex numbers in a very tiny circle around the origin. So at the origin, we know that we're realizing the minimum magnitude output. And now we're going to plug in complex numbers very close to the origin. So now the idea is to plug in numbers very close to 0. Now, how do you write a number that's very close to 0? You can write it in polar form. So you can write it in polar form. So you put z equals very small radius, epsilon, times e to the I theta. All right? We will have control over theta. We will control theta. and epsilon. Okay? And I'll show you, we'll develop how we're gonna do it as we go. So let's plug it in. Just plug in epsilon e to the I theta into the polynomial. Theta gang, exactly. All right? Yeah, theta gang. This is gonna help understand you analyze the stock market for sure. Okay, so let's plug it in. And our goal is to somehow deduce a smaller output magnitude. Okay, so you do this, you're gonna get P0 plus this next coefficient, and now plug it in carefully. Z to the m will be epsilon to the m times e to the I m theta. Right? M times theta. Okay? And then you keep going. But all I want to point out here is that whatever happens next will involve the fixed coefficients, p sub m plus 1 and so on. Those things are just fixed from the very beginning. And times epsilon to the higher power of m, to a higher power of m. That's all that matters in the analysis. So this, what matters here is that this is higher order terms in terms of epsilon. All right? You can go and keep it all written out if you don't believe what's going to happen next. There is no error in what happens next. I'm just going to skim for the rest of it. The rest is standard analysis-y type things. Okay, but focus on the first term, first two terms. That's what P of z is, for z very close to the origin. Okay, in a circle around the origin, epsilon circle around the origin. Now, let's write out the norm of this number. It's the number times its complex conjugate. Okay? And so if you write that out, okay, let me write the complex conjugate so that you have some practice. This is going to be this complex conjugate plus this one times, okay, epsilon is a real number, so nothing happens to it. E to the positive angle becomes e to the minus that angle. Plus the conjugate of all the other stuff. All right? And now you multiply, FOIL. And look what you get. You get P0 bar. That's the smallest, that was the smallest magnitude ever achieved. Pay attention to that. But then what else do you get? You get some funny stuff like this. It looks very complicated, but it's not at this stage. It's just a matter of tediously writing out the terms, okay? Now, the ... has, what I want to point out is the ... involves epsilon to a higher power than m. Each term is epsilon to a higher power times something that's, once I freeze theta, will be a frozen number, collection of numbers. Okay? Femvox, welcome. Hey, how's it going, Pro, I assume? Everybody? All right? So now, the great thing here is we still have freedom to choose theta. All right? And now I want to point out something. If you look at this thing is epsilon to the m times smash time. I'm doing analysis, dude. Like, I am so out of my element. I'm so glad you're here. Okay, yeah, so you do this, okay. Okay, so the first thing I want to point out, so the thing you want to observe about this is that this number right here, this is a real number. Because if you squint, it's a number plus its complex conjugate. It's this number plus its complex conjugate. So then you get a real number. In fact, you get twice the real part. Okay? Okay? You get twice the real part of just one of them. All right. In fact, you can collect all of the remaining parts, and there are a bunch of real numbers in the same sort of spirit as this. It's going to be a bunch of real numbers added together. Okay, but you don't actually need to know that. Okay. All right. So we got this real number, which is apparently the minimum of all outputs, norms, plus this real number times this one. And we have control over the theta. Okay? So now the point is that P naught and PM are non-zero complex numbers. So this is some fixed non-zero complex number. And we're about to just rotate it in a way that's convenient for us. So we can choose a theta so that this rotated complex number has negative real part. I don't care what you do, just choose one of those thetas. You can do that because we're allowed to rotate a fixed number in any way, any theta we'd like. Okay? So you choose that theta. The P0, the bar. Let's see. I think it's okay. P0 bar. Oh, did I? P0 bar. Ambrose 97. No. You don't have to minimize the entire. All you need is to choose a theta so that this real number, this real part, is negative. So see, what's frozen on us is this complex number. Because we inherited it from the beginning. And we know it's a non-zero complex number. By our P0 is non-zero and PM we assumed was non-zero. Okay? So that's a fixed complex number, and now we have the freedom to rotate it. That's what multiplication by e to the I theta does. I times any angle. So I want you to just rotate it so that this number is pointing backwards. Okay, that's all I want to do. We won't need to like find the most negative or anything like that. You can if you want. You don't need to though. Okay, so you find a theta that rotates this quantity so that the real part is negative. And then you just freeze that theta for the whole time. So then freeze that theta. Okay? And you write out with that fixed theta this whole expression. And then you get this thing. negative number, some fixed negative number, plus epsilon to the m minus 1 times another fixed number that's frozen on you. M plus 1, m plus 2. And now you choose epsilon small enough so that this negative quantity dominates all of the other quantities. So you choose each of these. Hey, look, epsilon is a small number, so higher powers of epsilon will not compete with lower powers of epsilon. Okay, so that's I'm just assuming you're comfortable with that level of analysis. You can go and try to learn how to use inequalities to epsilon deltas and so on to make that make sense to you. But that's it. So now the point is that in total, P0, this number, is smaller for a particular epsilon and theta direction away from the origin. And so you couldn't have had a minimum, you could not have reached a minimum positive output magnitude. So contradicts P of z naught, or whatever, P of 0 was minimum positive and strictly greater than 0. Notice where the strictly greater than 0, fits in. It's in this part, making sure we're rotating an actual complex number, not the 0 complex number. Good. So that we can actually start reducing the norm. Okay, so this is the actual corrected proof. There was some little bit of topology that you needed to know in the beginning to set things up. But then the latter part of the proof you can read in the book for all the exact details if you want. Okay, so the complex numbers are algebraically closed. You can't have a positive degree complex polynomial avoid 0. Okay? What was that? So that's the theorem, that the complex numbers are algebraically closed. Ambrose, is there an issue? Okay, if just trace through that argument, proof by contradiction. Okay, so in the last negative 2 minutes, I just want to say some things about algebraically closed fields. Some final comment, just some, not final actually, initial comments. So you think of an algebraically closed field as the kind of end of the road when it comes to solving one variable polynomial equations. But what I want to just say real fast is that the complex numbers are not the only algebraically closed. That's not the only algebraically closed field. Maybe you haven't thought of that many, but there will be certain subfields of the complex numbers that are already algebraically closed. So just a warning. There are subfields. Yeah, there are subfields. The one of them that'll be of great interest to us is one called Q bar, and what the bar indicates it's called the algebraic closure of the rational numbers. Okay, so and this Q bar field is not going to be all of the complex numbers. All right, it's a subfield, a strict subfield. Good. Does one use the axiom of choose to construct Q bar? Axiom of choice. Not if you smash time. Not if you assume that you have the complex numbers, because you just define it as the subfield of the complex numbers consisting of algebraic elements over Q. So that's why if you have C as an ambient world to do all of your math in, you won't then need to further invoke axiom of choice. The place that axiom of choice is needed is if you start with a random field and you don't have a global large field to work in, and you try to, from the ground up, construct the algebraic closure, that's when you'll need axiom of choice. Okay? So, yeah. So, for example, the algebraic closure of F5, the finite field with 5 elements, this will be another algebraically closed field. This is also an algebraically closed field. It's called the algebraic closure of the finite field with 5 elements. This is just Z mod 5Z. That's what we mean by F5. We use the F to emphasize we're thinking about fields. Like, we're in that way of thinking. So there will be some, like, you keep growing new numbers from F5's perspective, and you kind of reach an end. And that's an algebraically closed field called the algebraic closure of F5. Oh, hi Shrek, how's it going? Hi procrastination. Say you have 2 nested subfields in C. Okay, I'll say that. You have 2 nested subfields in C. Hope you had a good day. Are there examples where the smallest subfield is algebraically closed, but the middle one isn't? Middle ones isn't algebraically closed. But the big one is? Wait, why don't you just take C? Yeah, C. And then this. Oh, that's a good one. Yeah, I was thinking add a transcendental. So C, Q bar pi. Oh. Once you obtain algebraic closure, you get it for good only if you're assuming that you're taking finite extensions. So we'll learn about finite versus transcendental extensions, and that's why learning balance chose to take Q bar and then adjoin a transcendental enormous extension. Okay? So if you have an algebraic closure and then you finitely extend, you can't. You won't be able to finitely extend. But you can transcendentally extend, and then you most likely will not get a algebraically closed field again. In fact, you won't. For learning balances example. Great. Okay. So what my point is that there are more algebraically closed fields in this world, many more, than just the complex numbers class. There will be one called Q bar. That'll be the sort of main focus of our class. but we'll also look at other ones that are in some, they're kind of, you can't even think about them in terms of certain kinds of complex numbers. They're totally different types of fields, but they're out there. There's algebraically closed fields all over the place. And yeah, so for now, I'll stop there. You can try to prove basic things like a finite field can never be algebraically closed. That's a fun proof to think about, or problem to try to solve. But we'll eventually get to those kinds of things. I just want to say C is not the only example, because some students think that, you know, this is all there is for algebraically closed fields. There's all kinds of other ones. Okay. Okay, let me look at. When are we going to see that special polynomial? Oh yeah, I should put the special polynomial on the board at some point. Maybe I'll do that next class, because we'll be talking about polynomials next class. So I'll put that as an example, as a polynomial. So next class is basically starting chapter 3. And what is chapter 3 about? Boring facts about polynomial rings. Okay, that we'll need to internalize or remember from last semester. Okay. Oh, nice. Did the color change? Pandemic? All right. Did it actually change? Let me take a look at the. Let's see. Did it change? I think not. Yeah, maybe something's messed up. Something's messed up with the thing. Okay, who do I thank? Colored Binary, thanks for following 8 minutes ago. Hangs mate in 1 follows 16 hours ago? Okay. Well, that's interesting, right, Crow? That is interesting. All right, credits. Let's do the credits and then get out of here. I have to prepare for my commutative algebra class. I don't know what I'm teaching today. Okay, credits. Vixen. Hello, hello, hello. Hope semester is going well. Who else did I see that? Hangs mate in 1, I guess. New hangs mate. New friend. Wow. All right. Pandemic. Okay. Is the next class on Zoom? Yeah, the next class is no longer on Twitch. So that's development. Okay, you want to shout out? Okay, Malone. Theta Gang. Perfect. Executed. Emote. Okay. Yeah, no problem. No problem. Do you feel the like serotonin like going in deep or whatever? Hope you do. Okay. Who else was here? Oh, my students were here, of course. Hey, students, by the way, we can use tech in our Discord now. I haven't tried it, but you should try it. Go ahead and test out LaTeX on the Discord. Does one use the axiom of choice? Oh, wait. I just scrolled up in the chat. Okay, good. Nice proof today. Thanks, BMP. You have convinced me. Oh, Finbox. Okay. really what I wanted to so you should, I'm assuming the students are reading the book, so they'll be able to fill in any of the like non-important things that I sort of just that look, the epsilon term dominates, blah blah blah. But the real issue was the assumption that they made, which is that the polynomial function is proper. That's the topology term for inverse image of compact sets, compact. And they didn't do that properly. No pun intended. So I had to frantically mobilize. Okay. But there are way better proofs of it. Slicker, more beautiful proofs of the fundamental theorem of algebra, which is neither fundamental nor theorem in algebra, which is the often quoted joke. Okay. Smash Time was here. Smash Time was, I'm sure, banning all kinds of like trolls that were showing up for class. I'm sure it was a very difficult time moderating. Another was here. Another Saipet. RDL was here. I think those are the students that were here. Okay. And N. Burrows was here. All right, so here are the credits. Thank you all for stopping by. Learning Balance was here. I like that if K inside of F, if K over F is finite, and K is algebra. Oh yes. K is algebraically closed. Then KF has to be at most 2. Yeah, I wonder though if we'll be able to prove that. Probably, actually. Yeah, I think we'll be able to prove that. We'll have the tools to prove it by the end of the semester. We should. Yes, Crow. Wait, I thought that it was just true. Hold on. Maybe it's like characteristic 0 or something? Like separable? But then again, I'm vaguely remembering some example from my class when I took it, which was a degree 3 example. So maybe you're right. It has to be some but we'll use that kind of a idea for the algebraic proof of C being algebraically closed. You can use that kind of a fact, right? Silo 2 subgroups and the structure of Silo 2 subgroups, something like that. Is that what you're, I don't know if that's what you're thinking of, learning balance. That's what I thought of when I saw your comment. Okay then. So Vixen, Hangsmate, all of you, thanks for stopping by during the fundamental theorem of algebra A proof of it. And I'll see you next time on Wednesday, where we'll just do boring things involving polynomial rings. And then start talking about field extensions after that. Okay? So that's chapters 2 and 3 is where we are right now. All right, so I think I'm just going to do a hard, unless, wait, is Professor Peter or someone on? I don't know. Let's see. I think. Oh yeah, Crow. Wait, Gath is on. Does this work? No, that doesn't work. Ah, damn. No one's on. Okay. Mine is next week. That's pretty late. Wait, are you in some sort of quarter thing? I was thinking of Cake on Red's Art and Schreier notes. Oh, I don't think I've read those in any kind of. I don't think I know what those are. Yeah, nope. Ah, okay. So your semester starts a week. Wow. University of Buffalo. NYC. You're in New York City. Oh, I did. I think I knew that abstractly. I thought you were either there or in Chicago. I don't know why I thought I had placed Crow in Chicago, but you're in NYC. Oh, okay. Okay. I just placed you in some big city with skyscrapers. Yeah. I don't know why I thought of Chicago. Oh, more NYC people. That's good. Oh, maybe you all can. Okay, maybe is Mikey on? Maybe I can dump you all there. How do you spell it? There you go. There you go. Awesome. Let's go check out New York City, everyone. Let's go check out New York City. All right. I'll see you guys next time.